Okay, perfect. Yeah. So like it's a pleasure to have Gerard here. So he has recently done this beautiful work on SDP bounds on quantum codes, and mm, I mean this makes the region tighter of like what kind of like about valid codes that can exist and so on. I think there are many follow-up works that one can do from here. I mean, already there are many open questions that Gerard and his co-authors have mentioned in the paper. So Gerard, basically, he recently, I mean, he's a senior PhD student in Poland, about to complete his PhD, like, soon. And he has done this amazing work on SDP bounds on quantum codes. So it's my pleasure to have Gerard here. And Gerard, maybe you can do the screen sharing and maybe present your work. Yeah.
Yes, thank you very much for the invitation and for giving me the opportunity to give this talk. And I will start now. Let's see if I can, if it works. Okay. Now the problem will be sharing the screen because I don't know why it's not appearing.
So you can go like near mic, like there is an option called share. You can use that to share.
I'm doing this, but it doesn't appear the screen I open the PDF. It's possible if I send it to you and then you open it, or
that is also possible, but maybe I think that might be inconvenient to you, right? I mean, I can do that. I mean, that's perfectly fine. We can do that as a last resort, but maybe see it's okay. So something happened, but then it stopped.
Yeah. Wait. No. Wait. Now I had. Okay. Do you see the screen now?
Yes, I see it now. Yeah.
Okay.
Yeah.
So you see it correctly and everything?
Yes. Everything is fine. Yeah.
Okay. Okay. So as the presenter told, my name is Gerard Anglès. I was doing the PhD in Krakow. Well, I'm doing still the PhD in Krakow, but I will defend soon. And I will explain this last work I did during my PhD. Together with my supervisor, Felix Huber, now is actually in Gdansk, Poland also. I'm a collaborator, Andrew Nemec. And the title is Semi-Definite Programming Bounds for Quantum Codes, and I will try to explain a bit more the results of this work and the motivations and all the mathematical techniques we use, because I think there is a bunch of them to explain. So first of all, I will focus in the first motivation that there's a fundamental problem in coding theory, which is basically determining the maximum size of an error-correcting code. The size of the error-correcting code is basically the number of how many information you can codify in your code. So actually, it's an interesting question to ask, because more information you can codify, better will be. So in particular, we are focusing our attention in not only from error correcting to quantum error correcting codes, which also has some handicaps, and in particular qubit quantum correcting codes. So the question that we ask in the beginning of this talk is, does a qubit with quantum code with given parameters exist? I will specify which parameters we're looking into, but one of them, as a spoiler alert, will be the maximum, the size of the code. And our solution is we propose a complete semi-definite hierarchy for the existence of the qubit quantum code to exist for a given parameters. What I mean about semi-definite programming hierarchy is basically a code exists if and only if each level of this hierarchy is feasible. Okay, and from this solution, if you take an instance of this semi-definite programming hierarchy, we found three results that we want to highlight. So the first one is the result A, which is that the lowest number bounds the existence of self-dual quantum codes. I will explain what is a self-dual quantum code. It's a particular type of quantum code. The lowest number has a relation with classical error correcting. So I will also explain this relation. more or less. And the result B is that asymmetrization, if you add a minor variation of this lowest bound, recovers what we call the quantum Desartes bound, which kind of recalls what is the classical Desartes bound. And this also happens in the classical case, where the lowest, if you average over the lowest bound, it converges to the Desartes bound. And the result C, is that by taking this relaxation and then you averaging over the Terulician algebra, leads to something that you can compute. And actually, we have that if you compute this SDP, it proves the non-existence of particular quantum codes. So this is basically the resume of all the talk. And now we'll enter in the details. Just
So
mentioning
basically, this second bond is like you can obtain it from lowest bound. Like, I mean, is it like the same SDP, but you add some extra constraint or something, or get rid of some constraint?
So basically, you take the lowest bound and then you add some constraint, extra constraint, which is like an easy constraint to add. Like, it's different from the quantum case, but in the classical case, for example, you add basically that all the entries are positive, and then you average, and this leads to the Desartes bound.
So basically, lowest bound is a relaxation of this Desartes bound.
Yes, even though in the classical case it's a bit more tricky, this because actually the Desartes bound is stronger than the lowest. But in our case, since when you average over this, when you do this symmetrization, we lose some constraints. The lowest bound, the quantum lowest bound is stronger than the quantum Desartes bound.
Yeah, I mean, another thing, like, let's say, maybe we will explain later, but just see, because we are on the slides, we try to get the main message. So lowest theta number is one number that you get by, like, from SDP for a given graph, like you can define.
Yes.
And it's an SDP. And you get, let's say, so you do it for pentagon, you get √5 or whatever, like there, and there are all these lowest theta numbers.
Exactly.
Now, this number, I mean, how do we know that, it bounds the existence of self-dual code? Like, I mean, existence is a binary thing, right? I mean, exist or does not exist?
No.
So is it like, some cutoff or something like?
So it means that basically, if you have this number being higher than some value, then we don't know anything, and if it's less than this value, then we know that doesn't exist.
Okay. So you have some kind of a cutoff, then like if
exactly,
it's less than something,
exactly.
Then that gives you the existence. I see.
Yes,
I see.
Okay.
And you're saying that there is another relaxation which for some particular quantum code, but the first one will only work for self-dual quantum codes.
Yes. But we will go into the details about these things. Yeah.
I see. Yeah. Sure. Yeah.
Just to mention that the lowest number was proposed with this paper of Lowash, and the Terulician algebra, this technique of averaging that is applied in classical code was here.
I mean, in particular, this Lowash paper, in the Lowash paper, it's called standard capacity of a graph. And
yes,
he
exactly.
did it for 5 cycle, and for 7 cycle, it's still an open problem.
Yeah, I know this. Yes,
the standard capacity. Yeah.
That is another thing to take a look actually in the future. Okay, so now the question that we can ask is how we mathematically write this question. The question is, does a qubit with quantum code with given parameters exist? And the thing is how we write it down. So first, I will define very briefly what is a qubit quantum code. I will define a qubit quantum code that something that encodes a k-dimensional Hilbert space to an n-qubit Hilbert space. And the important object of a quantum code is the projector that I would call pi, that is a k-rank projector that basically projects onto the code superspace. This projector lives in an n-qubit Hilbert space and is a projector of rank k. Okay, that is the important is that we will take a look in this object later, because to a quantum code to exist, it needs to exist this projector, otherwise will not exist the quantum code. And then, like, if you take a state that is encoded in this code, and you send it via noisy quantum channel, this will induce errors to this message. Okay, this is the scenario of quantum error correction. The important here now is that we have two parameters, right? You have the n qubit, this n, that is the number of qubits that you have of the bigger space, and you have k, which is the size of the code in this case, because this is how big the message that you can encode. And the third parameter that's important is, okay, how good is this code? So, and here comes the distance. So a quantum code has distance delta if corrects errors acting to the delta -1 divided by 2 qubits. So we can denote that a qubit quantum code is basically with this this notation that is n, k, and delta, and this little 2 that is in there is basically because we're working in qubits. So we will define, we will work with this notation, okay, by defining for quantum codes. Okay, so the last slide we finished with the distance, the concept of distance, but the question that we can ask is, okay, how we determine this distance? How good is the quantum code? Is an important question. So first of all, this distance is defined with these Cornelius-Frank conditions that are in the title. But for understanding these Cornelius-Frank conditions, we need to define these two things. First, there's an n-qubit Pauli basis, which we denote by Pn, and it's composed by all tensor product of Pauli matrices plus the identity. This takes like the size of 4-line elements. For example, you have this E that is basically a tensor product of X, I, and Z and identity, and it belongs to this P4 because it has four tensor product. So then the next one is the weight, which is the number of non-identity elements from this Pauli. And basically in this example, the weight is clearly 3 because we have 3 Paulis and 1 is the identity, so the weight is 3. So here comes the Cornelius-Frank conditions. So this was stated in this paper on Kinil and Aflam. And basically the first sentence is given a code space projector pi. That means that has rank k. So given that this thing exists, okay, a code has distance delta if and only if it fulfills the following requirement, where basically you have this sandwich of the error needs to be proportional to the projector for all errors that are less than the distance, where this E is the Paulis and this alpha is basically a complex number. So you can understand here is basically you want that the action of the error needs to be trivial in some sense. You can like maybe think about this kind of condition like this, because if you have an error in the project, what is the action of this error? You have something that is trivial, which is the same projector, proportional to the same projector. Okay. What I wanted to tell now is that actually is related with one of the questions, that is the different types of quantum code that was asked before, is basically there is one definition that is important in this work. Is, well, first of all, a code is pure, that you don't need to confuse a pure code that a pure state is not the same. So a code is pure if this alpha is 0 for all the errors that are weight between 0 and delta. Okay, and in other words, you can basically pack this condition, but the trace of A pi is equal to 0 for this range. Okay, and then a code is self-dual if k is equal to 1 and is pure. So it needs to have the two requirements. So if like the message that you encode is just 1, k equal to 1, and it's pure, it means that it fulfills the following constraint. And we will use this constraint later.
What was capital K?
K is the size of the code.
K is the size of the code.
Yeah, it means that you are basically you have just one state.
No, I mean it's not the size of the Hilbert space, like I mean the logical space or something.
Yes, so the size of the Hilbert space we call it the size of the code because it's the number of the information that we encode.
So is it like k equal to 1 means that you can protect one logical qubit? Let's say we're talking about
no. That is important. We are not encoding qubits. We are encoding Hilbert spaces. So k equal to 1. It means, I mean, that is a bit maybe it's a bit using now this concept of pure. So a k equal to 1 is basically a pure state that has some correction, some error correction. For example, this state if it happens some errors, you can still recover the full state by doing some.
So then, I mean, so if you're saying that, it's not, if it's just one state, then a self-dual code is basically just a code designed to protect one state, right? Just one state.
Yes. Yeah, you don't have even like a qubit and anything. It's just one state.
Like,
so
let's say it can go to just plus state, but it can't protect 0 or 1, for example.
No, because so actually, like k equal to 1. So when there is like a type of self-dual codes when there are things that have maximal distance, which then you have like a relation with AME states. So an AME state is a self-dual code. It's a type of self-dual code. So there is a relation with
normally for self-dual, you will want the code and the dual code basically.
Yes,
if let's
they're
say
equal.
Same, then you call it self-dual, right? But
yes.
So what you wrote if, which means that it implies that the code is self-dual, but it's not is it a sufficient condition also? Sorry, necessary condition also, that k equal to 1 and pure, or I mean like, or is it just a sufficient condition?
So I think that the self-dual codes are defined to be k equal to 1 and pure. But because I think that, yeah, because okay, so that is what I understood is that, because these definitions of code are a bit tricky sometimes. So k equal to 1, it basically implies that there is self-dual, because the a and b enumerator are equal. But I will explain later what it is. But this means that you have this relation of the dual code. But I had a feeling that this is only because it reminds to the classical case. Because you have, in the classical case, you also have 2 enumerators and you have this thing. And the pure is because you need to, like, it's kind of trivial, the Coney-Laflamme conditions, if you don't impose that they are pure. So in order to not make it trivial,
I mean, do we know any quantum error correction code that is self-dual?
Yeah, of course, like all AME states, all absolutely maximal entangled states is a type of self-dual code.
A particular, even a state is a self-dual code. Okay.
Yes, exactly. Yeah. So for example, if k will be equal to 2, then you will code a qubit, because you have 2 states.
Exactly.
It's a 2-dimensional Hilbert space.
Yeah, I mean, somehow k equal to 1 is like very restrictive for error correction purposes, I would say.
It's because you can, well, you have this in the AME states, you can see clearly, like the information is like kind of redundant in some sense, because it's maximal entangled.
Okay, anyway, maybe you can explain more later. Yeah.
I mean, I will not explain so much in the concept, but maybe after the talk I can try to explain better, because this concept is just like where you're working with self-dual. This is a definition that is in the literature,
somehow not able to appreciate the motivation for self-dual code in the quantum field. I would like to, let's say, protect 1 qubit, 2 qubit, 3 qubit, like, I mean, I would like to protect some information. K equal to 1, it's mean like there is just one state, like, I mean, that's like very restrictive, right?
It happens. It's a state that it happens some error, you still can recover the state. You can detect it.
Yeah, but then in that case, like I can just do, if you already know the state, and for that you want to design a protocol, I will just prepare the projector and I will keep measuring and like I will get that state. Right? I mean.
Yeah. Okay. Yeah. If you know the state, yes. But if you just know that it's a code, you don't know. Yeah. I understand the thing is it's a weird, but I don't know what was the clear definition, but I mean, one motivation is that the code is basically an absolutely maximal entangled state. Well, a self-dual code, not all self-dual code, but the ones that are maximal, they are absolutely maximal entangled states, so they are related to actually states that are maximal entangled or has some parties maximal entangled. So the motivation maybe comes from this fact that there is this relation, but I don't know if there is more motivations about it. Apart from this part that, okay, you have a state and is an error happen or 2 error happen, you still can recover the state afterwards, because there is this maximal entangled property. Yeah, so it was a bit weird for me also. Like I was very confused in the beginning. Like there is plenty of definitions of codes and
yeah, and it's like I would like to protect at least one qubit, right? I mean, and I do not know the state of the qubit. Like that's what the error correction is for, right?
Yeah,
But I
yeah,
yeah. Mhm.
yeah. Here you know that you have one state, but you don't
Yeah,
need to know the
but
state.
that
You know
state,
you know the characteristics of the state. You don't know the state. It can be a state that you want to keep there forever, and you know that if happen one error, you still can recover the previous state. So imagine I send you a state that this state has these properties, but I don't tell you which state it is.
and also like for this purity, like what does this is also
No,
classical motion, right?
yes, I think
So
yes. So it's called pure, but don't relate it to actually a pure state.
yeah,
Yeah.
okay,
Yeah, it's
okay,
confusing because it's like a core is pure, but then a self-dual core is related to a state, a pure state. So yeah.
okay,
Um,
okay.
okay, but for now, the only important is that there exists this kind of codes that has k equal to 1, and they are pure. Important, this k is the size of the Hilbert space, not the number of qubits, which is also something that is confused here. So you have if k is equal to 2, then you will have 1 qubit. Makes sense? Okay.
Hey, so can I just ask a quick follow-up question? So
yes.
if k is only equal to 1, then this projector is going to be a rank 1 projector, right?
Yes, it's a pure state, yeah.
All right,
yeah.
Sounds good. Thanks.
Okay, so now the feasibility problem can be written in the following way. So the question now is, does a qubit with quantum code with parameters n, k, and delta exist? And we can organize this optimization problem like the follow. Find a projector, because it's subject to pi square equal to pi because the projector, that the rank of this projector is k because trace of pi is equal to k, and it fulfills these Cornelius-Frank conditions. And the thing is, like, we finish here. We have this optimization problem. We have that a code with parameters with these parameters exists if and only if this program is feasible. Problem of this is that it's very hard. There is the main problem is that you have quadratic constraints that you don't know how to deal with. This pi square equal to pi is hard. You have a very bad scaling because at least it's 2 ln because it's this projector has 2 ln to 2 ln size. So we don't know how to tackle this problem. Okay, so what is known about this question? How people tackle this question? And this is related to what one of the questions from the beginning, with quantum weight enumerators and what we will call linear programming bounds. So first of all, the Cornelius-Frank condition that we saw before can also be reformulated in terms of these enumerators. These enumerators are basically, if you can see here, there is the A and the B enumerator, and then you basically calculate this quantity that is the trace of E pi, and then multiply by the trace of E pi, and then basically you first multiply, you have pi error, and then you do the trace of all. And then you average over all the errors over that has the same weight. Okay?
I guess in the LP case, I think they're called like weight enumerator and dual weight enumerator, right?
Yes, exactly. So actually, it's self-dual because for self-dual code, B is equal to A.
I see. Okay, I see.
That is what they call self-dual. So you have these two quantities that are called quantum weight enumerators, and there are also something extra that it's important to know, is that they linearly relate with something that's called the quantum McWilliam identity, which basically relates one to another for B. So the remark is that the Cornelius-Frank conditions can be formulated only by A. So if I take a projector pi and I calculate A, I can check if this pi is a projector of that is related to a code of some distance. Okay, by checking this condition, this Cornelius-Frank condition, is completely equivalent. But again, it needs to exist P. So I need to do pi. Pi needs to exist in order to check these conditions. So now the question can be approximated by this linear programming bound, which is a very sketch scenario. So you need to find a bunch of parameters, this AL, which is, you don't need to confuse it with the previous A, is an approximation. These parameters is find some bunch of parameters that approximates this A enumerator such that it fulfills the following requirement, where B is defined by this McWilliams identity.
So basically, let's
this,
say this is Gerard. So let's say if I, sorry to interrupt, but let's say, so basically if I think of a different kind of code, let's say dynamical code or approximate code or subsystem code, then in these cases, basically the nil-Laplum condition will change, right? And
yes.
then basically in that case, one has to look at, like a modified version of a different program from here. I see.
Yes, I guess there is literature about the approximately quantum error correcting codes and these kind of things, and you can also procreate a linear programming bounds of that. I don't know if they are that easy. Maybe it's more complicated, but yeah. Basically, this program it says that this problem is invisible, then the code doesn't exist. If it's feasible, you don't know anything, because you have some A's that are compatible to this. This A is compatible to this A enumerators that depends on the project. So how we improve? As it was spoiled in the title, we basically promote this linear programming bound by SDPs. A linear programming bound optimized over linear constraints, semi-definite programming optimized over the cone of positive matrices. Okay. So now we need to put a different framework that is this is the framework where we used to have a complete hierarchy. Okay. So now let's imagine that we have a program like this. So you have basically a maximization over a Hilbert space, a set of operators that lives in this Hilbert space, and a quantum state with support in this Hilbert space. And we have some constraints, and we know that these constraints can be thought as a polynomials of operators over expectation values of rho. That is this state. As an example, you can, for example, have f of two operators. It can be thought like this, for example. This is a polynomial over expectation values, where the expectation value is basically the trace of this operator multiplied by the state. So if you can have a problem written like this way, where the constraints and also the objective function, that is the thing that you're optimizing, is expectation is a polynomial of expectation values of the operators over rho, then you can use the statement of the state polynomial optimization that was introduced here in this paper, that it says any program that can be written in that way can be approximated by a sequence of semi-definite programs. Okay, and this sequence of semi-definite programs fulfills two requirements. First, it's a hierarchy, which means that the level L is as strong as the previous one, but also harder. And it's complete. It means when this L tends to infinite, if you take of this sequence of semi-definite programs, take the L tends to infinite, you have a hierarchy that converges to the optimum. And this is only valid when these operators are bounded. Okay, so if you can find an N that is positive such that this sum of operators is bounded. Okay, so if it converges to the optimum, it means that you actually solve the problem. This is not anymore an approximation. Okay, so in some sense, it's like a guidance. You know that if you go in this higher and higher, you will actually find the solution that you are looking for. And more the genius construction then allows them to construct this Hilbert space, these operators, and this state from the solution.
Yes.
Once you have this solution, okay. Not always needs to be in the infinite. There is like some criteria.
So this is like NPA hierarchy, right? You have all of these moment matrices. Which side will keep increases, and
is the NPA hierarchy with the difference that you can have expectation values here. So it's different. NPA hierarchies, you don't have expectation values of polynomials.
I see.
And this is something that is important because we use this. Like that is the fact. This is called also scalar extension. And there was some paper, I don't remember. I cite this paper because it's the paper where they demonstrate that this is a hierarchy and it's complete. But you have something that is called scalar extension.
But like Gerard, like in NPA hierarchy, there is this rank look criteria, right, which tells you like at which level you have already achieved.
Yes. You have the same. You have the same.
Yeah, you have the same also here.
Yeah. I think you have the same. The thing is like for now, since I didn't use it and anything, I know that it exists, but it was not the point of the research. So I didn't go into the details because I think it's also very complicated.
Okay.
But yeah, sure. So there is for each problem there exists this optimum that you don't need to go to the infinite. Exactly. Okay. So now the question that we want to ask is: you remember that the problem that we wanted to solve is this one, and we want to know if this problem can be rewritten as is kind of expressed like this. So we want to know if our problem is a state polynomial optimal friendly, let's say. And here I changed something regarding to the previous slide. I just changed the maximization for find because I include this function as a constraint. But you always can do that. So the thing is, the problem that
I'm saying it's a feasibility problem.
Yeah, exactly. We changed the optimization to feasibility, but it's the same part. It's a state polynomial optimization problem. So the thing is, we want to find this hyperspace, these operators, and this state such that fulfills this constraint. So if we can write this problem as this, then we have a complete hierarchy. And now the question is how we write projector constraints and Cornelius-Frank conditions as something like this. First of all, the Cornelius-Frank conditions are polynomials of expectation values of pi. And you can see this because, well, this term is actually a polynomial expectation values because you have these are expectation values. So they are polynomials of expectation values. And then you sum over. So for now, for this, it's okay. And then you apply McWilliams. This is a linear constraint. So they are linear related, sorry, A and B. So you can have the following constraint that is the Cornelius-Frank conditions are also polynomials of expectation values. So we packed all these constraints like with this C1. Okay, now we identify C1 as a polynomial of expectation values that determines the Cornelius-Frank conditions. But important here, it depends of this. It means that these are Pauli's. So because otherwise this doesn't work. The second fact that is a bit more tricky, that I will sketch a bit how we derive, is that the conditions for a state being proportional to a projector of rank K, are also polynomials of expectation values of Pauli's. And this can be seen in the following. So a state proportional to a projector pi of rank K a state is proportional to a projector of rank K if and only if it fulfills the following requirement. So it means that the trace of this rho to m is equal to this 1 divided by k m minus 1. And you can see that by taking account these two conditions. The first one is the swap discomposition. So you decompose the swap over the Pauli's, and you know that the swap can be decomposed by this. So the swap is the exchange of two parties. And then you also know that this object here, this trace of pi m, can also be written as the trace of this kind of object, this Van object that is basically the cyclic permutation multiplied by a tensor product of rows. Okay. So if you plug this swap here, because the cyclic permutation can be decomposed by swaps, then in the end you have something that is trace of an expectation value multiplied by a trace of expectation value, and this is a sum over a lot of elements. And this also is a polynomial of expectation value. So you have this C2. So we pack first now C1 and C2. C1 is Cornelius-Frank conditions. It marks the distance of the code. C2, it marks that the state is a projector. So it seems that we end this. So for now we have the following. You have that the distance is fixed and the projector is fixed. So we apply this, but there is a problem here. That is that for applying C1 and C2 and to be if and only if conditions, because the Cornelius-Frank conditions are if and only if conditions, and also the projector constraints are also if and only if conditions, we require that these operators are Pauli's, but they are not Pauli's, because of the polynomial optimization optimize over the full space. So optimize over the operators also. So we cannot fix the operators. We cannot force these operators to be like Pauli's. So they are not Pauli's. But, well, we will basically forget about this, and we just pretend that they are Paulis. So we'll include all other constraints, and we'll pack all these constraints that is basically, they have the same anti-commutations and commutation relations. They behave exactly the same like Paulis. And we now have a bonus. So the quasi-Clifford algebra that is stated in this paper makes that all the operators fulfilling this C3 constraint are isomorphic to Paulis. So by just considering that these Paulis are that these operators are like Paulis, we actually make them Paulis. So now the problem is kind of solved, because now we have optimization problem where C1 fixes the distance, C2 fixes that is a projector, and C3 fixes that we are working with Paulis, so it makes the C1 and C2 an if and only if condition. So now we have that the state polynomial optimization optimize this following problem, and we know that this problem is bounded because these operators are bounded because they are Paulis, so when you multiply them is the identity. So then we can approximate the following problem as a semi-definite problem hierarchy that is complete. So that is the first solution. The solution is we have a complete semi-definite programming hierarchy for the existence of a cubic quantum cone with parameters n, k, and delta. Now, the question that one can ask is, well, yeah, but this hierarchy, how it looks like? So how is this hierarchy?
So basically, like, sorry, it's just a question, like Gerard. So
yeah.
let's say when you, so can you go to the previous program? Yeah, this page here. So let's say you run this, and okay, so when you run this, you will get some Hilbert space, you will get like bunch of AI, and you will get some density matrix.
Exactly.
And using that, but this H is the space where, like like what is this H? H is the projector.
So you mean H? This is a Hilbert space.
Yeah.
And rho is a project as a state proportional to a projector.
Rho is a state proportional to the projector.
Well, I mean, rho is any state, but C2 fixes it to be a projector.
Like normally in the Bell case, like Bell measurements and like Bell scenario and all, these AIs are, like, I mean, and BI, they will be Alice and Bob measurement, rho will be density matrix, H will be, like, but here, like, I mean, the way you formulated, rho will be something which is, you're saying that, it's proportional to the projector, like on the code space, and AIs are basically all of these, like, weight enumerators.
Yes, but the important is that it's because there is these constraints. So C1 fix that is a code, the distance sum, and C2 fix that is a projector, and C3 makes C1 and C2 even only if conditions, and fix the Hilbert space to be qubits.
I see. But it could be very much possible that there are multiple codes, like which satisfy this condition.
Yeah.
Like I mean, let's say, like, you find some feasible solution, but I'm saying the feasible set need not be unique, right? I mean, it could be there could be many codes there.
You're completely right. But since we are not caring in that sense because we want to know if something doesn't exist. So I mean, for the existence, it's true that then, like, if you want to find which code is actually there, then yes. But also, like, going to this, like, very huge hierarchy, also it might be a problem. You need to imagine that, well, now we will see, but the scaling is terrible. So this will be the next topic.
No, I'm thinking of some follow-up work on that. So that's why I'm like,
I
am beyond like, motivation to ask. So for example, normally in Bell case, like, you have some feasible set. In a feasible set, you are trying to, like, maximize some, there is a metric of success or whatever. And then let's say when you achieve the maximum value, you can ask, is the AI and rho unique, which correspond to that state? So maybe that will prove that, like, the underlying code is actually a unique code, something like that.
Yes, that might also be. I agree that this can be. But actually, I think there is infinite type of codes, because you always can have a unitary average. So you can have a projector, and then you can run any unitary, and it's still a projector. So I have the feeling that you always have infinite number of codes, because you have a unitary that you can map one projector to another projector.
No. Like when we say unique, like unique up to some isometric degree of
Okay. Then yes. Yeah. So now what we want to maybe I will be a bit out of time actually. So now what we want to see is how this hierarchy looks like. So if people knows about NTA, I think it will be easier to understand this section. So basically, you take a matrix M and you index by monomials of this omega. By monomials, I mean things that like this. So they are not sums, they are not polynomials. They are basically expectation values and operators multiplied. So you index this matrix, and then we say, well, let's just make this matrix approximate the following value. So each entry of this matrix, we will take it like this. Okay. So we approximate the following value. But these elements here, they are not equal to these elements. They are just approximate. So if you want to approximate M as it behaves like this, first of all, we need to enforce that M is positive. Why? Because if a matrix would be like this, then it would be positive. Even if you want to approximate this M, then M needs to be fixed as positive. Another thing that we want to enforce is that, well, when MEJ is equal to MEKL, when this happens, because we want to approximate this value. So that is we need to impose that this is happening, right? And then the last one is that we want to enforce all possible constraints, this K1, K2, and K3, as it was written like it that way. So it's basically pretend that this matrix is a matrix written like which entry is like this, and then try to enforce all possible constraints plus the constraint of CK. These constraints are like the ones that we derived before. So if we do that and we write this matrix like this, and I take this picture like this of this matrix, then what we can do is first define a monomial degree, which is the number of operators appearing in this monomial. In this case, this has monomial degree 2. And then you you take a matrix, and we put a subindex L, a superindex. And this is the matrix indexed by all the monomials up to this degree L. And then we say that this L determines the level of the hierarchy. So one instance of this hierarchy, one level of this hierarchy, of this qubit quantum code hierarchy will be this. So find an M, L that is positive, such that it fulfills this condition because we're approximating this object that we see before, and it fulfills this that C1 and C2 and C3 I applied in this M, L. Okay, so this is the instance. And now to sum up and finish this part of the hierarchy, basically we had a feasibility problem. We rewrite this feasibility problem as something that is equivalent, that is this one, and then we basically make an approximation of this problem. So these two are equal, so it's the same problem, like just written, and this basically approximates the equivalent feasibility problem. Okay, so this basically is a one of the levels. It approximates, and when L tends to infinite, we have like a solution, an optimal solution. So now, that is very beautiful, but what we can do with that? What we do? So basically, from this hierarchy, we take a paradigmatic relaxation. Okay, this relaxation is the one that is indexed by this. So now here we change the e's with the a's with for e's, because since we're working all the time in Pauli's, and C3 we know that fixed the operators A E to act like Pauli's, we just like now index it by e's. I mean, we can keep the a's is the same. It's just like more convenient for the explanation to use just the e's, because now we just say that the things are approximated to Pauli directly. So we indexed this matrix by all Pauli strings that is for a line. Then we say that each entry gamma approximates the following value. This is basically the sandwich that we see before, the sandwich of these omegas. So, but with this indexation, okay? So we say that this gamma approximates this value. And now we impose the conditions. The first is the gamma is positive. This is the same that before. Second, the gamma 0 is equal to 1, because we are considering that E0 is the identity. Is from all these Paulis, we consider that E0 by convention that is the identity. So we know that gamma 0 is the 1. And then one thing that is very important is that these two elements are equal. We can see here from this, you can see that these things need to be equal, because if you put that they are equal, then you have an identity here. So this is the term that it results, or otherwise this is the identity and this is the identity. So you basically have the same. And the important here is that if this guy approximates this term, if you sum, you average, you have the A numerator, so you have the linear programming bounds. So the importance of this relaxation is that it includes the possibility to add the linear programming bounds. Okay, so that is something that we wanted, because we want something as strong as. The next constraint is a bit more tricky to think about it, but the thing is that this gamma, this matrix is 0 for when this power is anti-commute. Okay, and you can see this because this term here that is approximated, that we want to approximate, sorry, is imaginary when these two anti-commute. So the real part is 0. And we know that if the matrix is valid, also will be the real part. So we are just considering the set of real positive matrix, because we know that one thing leads to another. So we have this constraint. We have, using the projector constraints, something very nice. The sum of the diagonal is 2ln divided by k. It's not something that you need to derive now, but I just show you that this is what it happens. And then you have other constraints. Okay, you have that, for example, the sum of all the elements is 4ln divided by k squared, but we don't care. Now we focus with all these constraints. Okay, that is important. All these constraints from gamma positive to C2. Because now we take this paradigmatic realization that the scale is terrible. It's 4ln, which we are not actually improving so much. So we have a matrix with 4ln. Before you had this projected this 2ln. And we take for set-dual codes. What was a set-dual code? Was a code of k equal to 1 that is pure. Okay. So now we have this indexing that I show here. I just resume all the constraints that we had before, except that, well, I put here the constraint of a 1 in the first element, and that here that is positive. And then, just a reminder, this is not all the constraints that you can add to this gamma, but we are just adding some of them. Okay, that is important. And then we have that this condition of cell-dual codes, C1, that was related to Conilla-Planck conditions for cell-dual code, includes this extra constraint. So now we have an extra constraint, which actually is very convenient, because if you think about it, we have just constraints are the sum over the diagonal, that the first element is a 1, that the diagonal and the first row are equal, and then you have zeros. When something happens, there is zeros. When this anti-commutes and it happens this, you have zeros, which are like very nice constraints, let's say. And this is related with the lowest number. So now I will just explain what we consider as the lowest number. So now imagine that you have a graph. It's a simple graph. It doesn't have self-edges and neither multiple edges. And now you basically want to ask what is the maximum number of non-connected vertices. And this is what is called the independent number of a graph, this alpha G. So for example, in this pentagon, the independence number is 2 because these two are not connected. Okay. And you cannot find 3 that are not connected of this graph. Okay. So the importance of this independence number is that it's very hard to compute it. So what you want is an upper bound. And this is where lowest number comes into action, which is that the lowest number is an upper bound of this independent number. And is an upper bound that is easy to calculate, or at least easier, because it's an SDP. An SDP can be calculated. This independent number is very difficult to compute. And as you can see, you are basically the lowest number is you take a matrix that has a 1 here in the first element, as the previous slide. You have that this M has in the diagonal the same elements that A in the diagonal, which means that the first row and the first row and the first column is equal to the diagonal. And then you have zeros. So actually, we can also imagine the following scenario. Now we define a graph where all the vertices are Paulis, except the identity. And we defined that two Paulis are connected when they are in the commute, or the multiplication of the weight is inside this range, or you have a self-edge when this happens. Remember that the lowest number doesn't have self-edges, but we are considering self-edges here. So we can define the following: theta number. It's not the same that the lowest number because it contains self-edges. But if you see here, you have a sum over the diagonal as before. Like the first element is 1. Then you have this equality that is also the lowest number, positive, and zeros when you have an edge. So the importance of this is that actually you don't care so much if you have self-edges. While traditionally self-edges are not defined in the lowest number scenario, here you don't care. Why? Because these two values, so for example, like this value of this graph is equal to the lowest number of the graph prime, where this graph prime is a subgraph without the self-edges vertices, which actually it makes kind of sense. So basically you basically take the graph and you remove the one that self-edges, and then you calculate the lowest number is the same that the problem that is here. Okay. So here, then we need to think in the following way. So that is the lowest number. This is our lowest like number with self-edges, and we also knew from this constraint that self-dual code must satisfy this condition. So actually we have the result. We know that if a code with the self-dual code and one delta exists, then this needs to be bounded, because this needs to be satisfied if a code exists. And as a remark, as we said before in the beginning, the lowest number for classical codes also bounds something related to the classical code. In this case, in the classical case, is the size of the classical code. In this case, for self-dual code, it bounds the existence.
So Gerard, like, maybe this is like a tangential question, but like let's say this gamma matrix which optimizes this lowest theta number for self. Let's say that optimal gamma is unique. Does that say anything about this self-dual code?
So here we're doing. So you mean that this gamma is unique? I think not, because you are just bounded. So if it's
no, you're maximizing, right? So
yeah. I think the thing is
the optimal gamma, if that is unique, like does that say anything about self-dual code? Like I mean, if that gamma is unique.
Actually, I don't know, because the thing is, like, if it exists, in principle, you don't know anything because you're approximating.
Because stuff. I wrote a few papers where I studied properties of such SDPs, where like we related it with some device certification thing called self-testing, and we had some results there. So I don't know. We can talk about it, but if you feel if it means something, maybe we can think about it later.
Okay. So I don't know, actually. I don't know because I don't know if it happens also in the classical case. Like, I don't know, in the classical case you
for the, like in quantum, because like let's say gamma is the optimal gamma is unique. Does this mean anything?
Yeah, I don't know, actually. If it's so, you know that when it doesn't exist, it means something. If it exists and is unique, in principle, you don't know anything because you're relaxing. So it might be that it exists, this gamma, but it doesn't mean that the code exists or anything. It cannot mean anything. Like, it might be that it doesn't exist still because we are not adding enough constraints.
Okay.
The problem that here is the relaxation. We are not considering, it's a feasibility problem, but well, in this case, it's like a maximization feasibility problem. But the idea is like to bound some existence. So I guess that because it might be that you find this gamma and then you add another constraint and you just discard it, because since we had more constraints to add, it might be that this gamma then is not feasible at all. Well, just terminal scale is terrible still, so we are not solving anything. It's just a relation. And now we will get to the quantum Desartes bound. That is like the last slides, 2 slides, I think. So first of all, now imagine that this index that we make arbitrary Paulis, now we map each Pauli to a 4-dimensional array of n elements. That is for we define with this for a line, which basically, so for example, you take this spiral string and then you map the y in 2, the z to the 3, and the x to the 1. So it's like a very natural mapping, I think. Like the identity is the 0. Okay, so now we are working with a matrix, this gamma matrix, but is indexed by these 4-dimensional arrays. Now we define the automorphism of this for a line that we denote by automorphisms of for a line. And then this is basically all the permutations over the n elements plus individually permuting each element, which I put an example here for clarifying. So basically you have this string, and you do a permutation, you swap 0 and 1. For now it's okay, and then you permute individually this element. For example, you take the 1 and you map it to 3. Okay, so this number of permutations that you allows you to do this are out for n. Okay, and now we define the action of this permutation to the matrix. This matrix that is indexed by these 4-dimensional arrays. So we say that a gamma applied, so a sigma applied to the gamma, then this element xi is equal to basically taking the gamma and apply this gamma to the coefficients. Okay, this is the action of these automorphisms to a matrix that is indexed by these 4-line elements. Okay, and then we average over. What means averaging? Which means just sum over all the automorphism of this sigma. The idea is that this averaging, it keeps the matrix positive because it's basically summing over change of basis, so it keeps this thing positive. And the importance of this averaging is that if you do it and then you add an extra constraint, this leads to the quantum Desartes bound, which is an LP, and we define it like this. And we define it inspiring this quantum Desartes for the classical case. So the Desartes bound, the classical one, is very similar to this linear programming by some minor modifications. So basically, you have this relation where for the self-dual code, you take the lowest number, you average it, and then you obtain something that is very similar to the Desartes bound. And we have another bound here that is like less strong than the lowest. That is, if a code with this exists, then 2ln is so exists, then this bound needs to be bigger than 2ln. Sorry. And just as a remark, this is the same that happened with the classical case, where lowest leads to Desartes. And this is the paper where they compare both. Okay. And now let's take the last slide. I will not bother you anymore. So now the key part, that is the symmetry reduced relaxation. So now imagine that instead of the automorphism of 4ln, we take out 0. What I mean out 0 is a subgroup, a subset of this out that leaves the all 0 string invariant. What I mean about all string invariant is that the zeros the zeros stay 0. So here, for example, it allows to do this permutation that we did here, but for example, do a permutation here, it's not allowed. The zeros stay zeros. That is more or less the key message. So this is the group, the subgroup, the subset, sorry, out 0. And then we do the same. We average over this out 0, and we define this gamma tilde. Okay, basically is the averaging over this out 0, where it keeps this 0 all 0 string invariant. So the importance of doing this averaging is that then this gamma tilde belongs to the quaternary Taylor-Origin algebra. This sounds very, very difficult, maybe, but it just allows you to block diagonalize then this matrix, reducing the size from size 4ln to n4. So that is the important thing. You're basically taking a matrix that you cannot calculate at all. You basically average over, and then you do the same. You try to apply all the possible constraints. Okay? And then we are including all constraints, not only the ones related to lowest. We add everything we can, like all things that we are capable to imagine and all the things that are possible. And then we can have something that is very interesting, that is we have that this reducing from 4ln to NL4, which is good. But also we have something that is very interesting, that the diagonal of this average gamma approximates the numerators. So we already know that the averaging also contains the linear programming bound. It means that it's as strong as the linear programming bounds. So that is the key point, because we know that we will not do something weaker. It can be that doesn't work, but at least it's not weaker. And also it's computable, because N4 is something that you can compute as an SDP. And this SDP actually, this proved the existence of quantum codes 714, 893, and 1054. And in particular, 714.
So Gerard, like, I mean, let's say, you know, like, I mean, so here, like, let's say if I just run LP, then
yes,
using LP is, like, I mean, does 714, like, you know, is it feasible? Like, I mean,
no, it's always feasible. Sorry, yeah. So the LPs are not discarding 714 as a code.
So basically, I mean, you know, concrete examples where this outperforms, like there's a rigorous separate. I mean, there is a, I mean, like,
yeah.
Give me 3 examples, right? So there is a separation between how powerful,
yes,
you know, like
yes.
the SDP bonds are than the LP bonds, I said.
So these 3 codes, they are not disproved with the LPs, the 3 of them. But the difference between these 3 is that the last 2, they were not known. They are new bounds. And the first one were new, that doesn't exist, but it was because it was disproved analytically in this paper. Okay, so the idea is like, okay, that is not that strong because it's not new, but it's still you have still like a program which allows you to discard more codes in the future. We know that what we are doing is stronger. Only by this we already know that it's stronger than LP, because LP is not possible to discard 714. So they are not strong enough. But we know that doesn't exist because this paper was come out in 2017, and actually from my supervisor, and it basically says that this code doesn't exist. But it's analytical, the result, which also is good because it means that it kind of matches, no, our bounds with this. And there is not a lot of proofs of analytical proofs of disproving codes. It's hard because I think this was one of the paradigmatic examples where like there were very little, so you still could do something analytically. Okay, so now let's just finish the presentation with summarizing the contribution and mentioning a couple of 3 outlooks. So the first is, well, we had this complete SDP hierarchy for the existence of a quantum code. That is the first part of the talk. Taking a pragmatic relaxation, we can include still all LP bounds, so that is a good thing. Problem is that it scales very bad. But it still can be symmetry reduced with the heterogeneous algebra, which actually includes still the LP, which that is the something that is very nice. And actually, this allows to disprove the existence of these 3 codes. These 2 were not known. This one was known, but analytically. Another result is that we have quantum analysis of the classical Lobach diamond and the Desartes bound. So that is also a very nice theoretical result. It's not like a disproving something, but it's like a nice relation with the classical case. And now the outlooks. The outlooks, well, we can prove the possibility to generalize to qubits. Now we're talking only with qubits. That might have some problems because there is this quasi-Clifford algebra, which is only work for qubits. So we need to someone needs to work it more for generalizing. Then another outlook is that, well, this Lobach only works for self-dual code. That is kind of weird. It would be nice to have some interpretation that bounds quantum codes the size directly, because here it's a bit weird because the classical Lobach bound bounds the size of the code, and in our case it's just bounds the existence. So it's because the size is fixed with k equal to 1. But yeah, actually we don't know. Also, like the self-dual codes, these k equal to 1 codes, they have some relation for classical codes or something like that. So maybe the relation why we have a Lobach is because there is some relation with the classical code that doesn't happen with pure quantum not pure quantum codes, no. So quantum codes that are just all quantum codes. And the third outlook is the we cannot tackle more general error scenarios. So for now, errors were all published because we wanted to compute distances and these kind of things. But we can imagine more general scenarios where we are just, so you remember that this hierarchy, you don't fix the operators. So it can be anything. So we can imagine graphs or scenarios where the operators are more general, not only published, and they are not that many, maybe 5 or 6 errors, I don't know. And then do some kind of like computation of SDP with that, saying, oh, what is the Hilbert space that basically corrects these things, these errors. That is some of the outlooks that are possible to do. And thanks for the attention. Sorry if it was a bit long. That is the 3 of us, and the paper is in archive since I think was August or something like that. Thanks.
I mean, you look different in the figure.
Yeah. It was a long time.
Okay.
A lot of things happen.
Okay. Yeah. So very, very nice talk. Huh? I think people already asked question. I think if there is a question, maybe please unmute yourself and ask. And if not, let's thank Gerard. Like, it was a beautiful talk.
Thanks.
I will stop the recording now. And yeah, let me stop the recording first. And yeah. Okay, so I have stopped the